Okay, we can start now. Good morning, everyone.
Good morning.
Today we are gonna learn about vector space. Last week we already learned about vector, right? And this time we want to learn. We'll learn about vector space. What is that? Okay, this is our definition. Let V be an arbitrary non-empty set. So we have this V is non-empty set of object which two operation. These two operation is are addition and multiplication. Multiplication by scalar. Okay, by addition here, we mean it just symbol depend on our set here. Every case we have different definition of our operation here. So later I give you the example. Okay, our set V here, we called a vector space if the 10 axioms are satisfied. Okay, we have 10 axioms here. If our set V with two operation, addition and scalar multiplication, satisfy all of these axioms, we call it our V is a vector space. For sure, you have to memorize all of these axioms. The first axiom, we can call it a close under addition. Why close? Because if we have two factor here, any factor u and v in v, then the addition u plus v here also in v. The second axiom we can call commutative law. U plus v equals to v plus u. The third axiom we can call associative law. And the fourth, there is an zero factor here. Zero factor here also depend on each case. Yeah, later I will show. Why we call zero factor here? Because our zero factor satisfy this property. U plus zero, our zero factor equals to 0 plus u equals to u itself. This satisfy for all u in V. And then the next axiom, for each u in V, there is an object, there is negative u here, such that u plus the negative equals to our identity here, zero factor. Okay, the sixth axiom, we call close under scalar multiplication. We have scalar k and u factor in V, then k times u in V. And the next axiom, we have k scalar, u and v are factor in V. So k times u plus v equals to k times u plus k times v. And this one, k plus m times u equals to k times u plus m times u. K and m here are scalar, u is vector. The last two axioms, k times m times u equals to km times u. U here vector, k and m are scalar. And the last axiom, 1 times u, 1 here is scalar, 1 times u equals to u. Okay, maybe I don't know how to memorize it. It depends yourself how to can easily memorize it. Maybe we can continue to the example so you can imagine it. Okay, the first example we have set v is n space. We already talked about it. With the standard operation addition and scalar multiplication in Rn. Do you remember the operation? Maybe I can write here. If we have u in Rn, u1, u2, until un, right? This is our factor u. If we plus with v, v1, v2, until vn, and then what we get? Addition operation in Rn, or n space, we get also factor, right? What is the first component here?
U1, V1.
U1 plus V1,
Plus
comma,
U2 plus V.
plus U2 plus V2.
yeah, U2 plus V2 until Un plus Vn. This is the standard operation of addition. What about scalar multiplication? We have k times u1, u2 until un. We get ku1, ku2 until kun. Okay, nah, for two operation, we get Rn, or n space is a vector space. I didn't write the proof. You can show by yourself, please. Why? I will show you for this second example. If you have set V, V is a set with a component 2 by 2 matrices with real entries. This V is a vector space with two operation addition, metric addition, and scalar multiplication is matrix scalar multiplication. Do you remember the operation? Okay, how to show this V is a vector space? So we have to show with these two operations, metric addition and scalar multiplication here, satisfy for all 10 axioms of vector space. Okay, firstly, we need to take any matrices here. If you take a look at this axiom, we need three factor, right? U, V, and W. And we
Uh-huh.
need two scalar, K and M. So I write it here. For any matrices U, V, and W, because this time our set is matrices. So I take it three matrices here. Matrices, all of matrices are in V. V is 2 by 2 matrices. So our U here, U1, U2, U3, U4, and same V and W. And for any scalar K and M. The first axiom, we want to show that U plus V is in V, right? So just write it down. Our U is U1, U2, U3, U4 plus V. And then we get this, right? This also 2 by 2 matrices. So it means this is also in V. So we already proved that axiom 1 hold for this case. What about axiom 2? Axiom 2, we want to show that this V with this operation satisfy commutative law. U plus V, we get U here and V here equals to V plus U. And axiom 3, just recall from associative law of metric addition, we get this. Is there any question up until here? No.
No.
The point is you have to memorize all of the axioms. Okay, next axiom we have, okay, wait, I need to erase this. Axiom 4, we need to find our zero factor here such that U plus 0 equals to 0 plus U equals to U itself for all U in V. Since our V is a 2 by 2 matrices, so our zero metric here also 2 by 2 matrices. But what entries for our zero metric here? We can easily guess that our zero metric here, all the entries are 0. Maybe some case we cannot easily guess what is our zero factor. So you can construct, maybe, wait, I need to write, okay, maybe I can write. In case you cannot find easily our zero metric, so we have to construct here. Maybe let 0, let our 0 equals to, quite, why Siri? Wait, I want to write 2 by 2 matrices. Maybe this one X, Y, and the second row Z, U. It's not good, right? Wait, where is, okay, this is our factor. Our matrix. This is our candidate for our zero factor. And then later, we can conclude that x, y, z, and u, all of it are zero. From where? Because we have u plus 0 equals to u. It means we have our equality here. We get u1 plus x. Quite difficult to type metric here. Wait, it means we have u1 plus x, the first component, first row, first column. And the first row and the second column, we have u2 plus y. And the second row, first column, we have u3 plus z. And the second row, second column, we have with u4 plus u. This equals to
So X, Y, Z can be any number or it will be 0.
what?
I mean,
This is our construction. If we don't have any idea what is our zero metric here, just in case you wait, why so difficult? This one equals to this one equals to u1, sorry, wait, text. u1, u2, wait, u3, and this one u4. Okay, for this equality we have, no, it should be
all in
one metric, right? So we have this equality, we get u1 plus x equals to u1. So we get x equals to 0. And u2 plus y equals to u2. It means y equals to 0. And u3 plus z equals to u3. It means we get z equals to 0. And so that's for u4 plus u equals to u4. We get u equals to 0. That's why we get our zero metric here is zero metric. All of the entries are 0. Okay, so it's just our contraction. So from zero metric here, we get this property, our identity property, u plus 0 equals to 0 plus u, we get u. Okay, the next axiom. Wow, okay, I need to erase. For each u in V, there is a negative of u, this minus u, our minus u. This also, maybe you have no idea what is our negative u. So you need to contract like before. So with this negative u, we get u plus negative u equals to zero matrix here. Our identity element at axiom 4. The next axiom, we have k and u. K times u, we need to show that k times u also in V, close under scalar multiplication. K times u, we have this. This is 2 by 2 matrices with the entries are real numbers. So we can conclude that k times u also in V. So axiom 6 hold. The next axiom, we need to show that k times u plus V equals to k times u plus k times V. By our operation, we get k times u1 plus v1. This addition operation, metric addition here. And then k, we get k here. This one we get k u1 plus k v1. From here, we spread into two factor, right? So we have KU1, KU2, KU3, KU4 plus KV1, KV4. This one equals to K times matrix U. This one K times matrix V. So we have this KU plus KV. Okay, any question up until here? Just follow our definition. Okay, next. Still, there are three axioms left. The next axiom, we need to show that k times k plus m times u equals to k times u plus m times u. Again, by operation in metric, we have this k plus m times u1. We have k times u1 plus m times u1. Then from here we have KU1. We spread again into two matrices. So we get K times U plus M times U. For the next axiom, we have two scalar here, K and M times U equals to here. The last axiom, 1 times U, this our 1 here, our 1 scalar here, times U equals to U itself. So since the all axiom of vector space holds, thus the set phi is a vector space. For sure with operation of matrix addition and matrix scalar multiplication. If we have different operation, we cannot guarantee is it still vector space or not. Depend on the set and the operation. The next example, I give you set that is not a vector space. We can continue, or you still try to understand this term? I don't think so. Just memorize the example. Okay. Next, this is our next example. A set that is not a vector space. We have phi is a two space and define addition and scalar multiplication operation as follows. We have u, u1, u2, phi, phi1, phi2, then define u plus phi here. This is a standard addition. But for scalar multiplication, it's not the standard multiplication here. We have k, scalar, or real number here. Then define k times u equals to k times the first component of u. The second component always 0. For the example, if we have u minus 1, 3, phi 2, 6, and our scalar is 4, then u plus phi, this is the standard operation for addition. So we have minus 1 plus 2, we get 1. And the second component we have 3 plus 6, we have 9 here. And be careful for this multiplication. K times u equals to 4 times u. Remember this formula. It means 4 times the first component of u. We have minus 1 here. The second component always 0. So we have minus 4, 0 here. Okay, if let me ask you if I want to determine minus 3v. So what is our factor here? Minus 3v equals to?
Equals to
negative 6.
Negative 6. The second component?
0.
0, always 0. So this is our minus 3v here. Okay. Can you guess this set with these two operations? Is this vector space or not?
Yes.
Yes. Are you sure? So you have to show that this operation satisfy for all 10 axioms. But like I said before, this example, a set that is not a vector space. It means at least one of the all axiom fail to hold. Okay, maybe we can start from the first axiom. Is the first axiom satisfied? U plus V is still in V. V here, two space. If we have U plus V, we have U1 V1 plus V1, comma U2 plus V2. Is this in R2? Yes. So axiom 1 satisfied. For this one, k times u, we have k u1, 0. This is also in R2, right? Into space. It means our axiom 6 hold, also hold. Oh, wait. Okay, like I said before, this addition operation is standard addition operation on to space, but the scalar multiplication is not the standard scalar multiplication. By this operation, the first 9 vector space axiom are satisfied, but not for the last axiom. If you take a look at this, k times u, the second component always get 0. So we need to find the counterexample here. The counterexample our purpose for to show that the last axiom fails to hold. Okay, for the example, if we choose u is 5 minus 3, then our 1 times u here equals to 1 times 5, and the second component 0. This is not our u, right? So the last axiom, axiom 10. Do you remember axiom 10? Axiom 10, we have
Okay.
for all u in V, we have 1 times u equals to u. Okay. Once we have u in V, one factor in V doesn't satisfy this equality, so axiom 10 fails to hold. Okay? So this V is not a vector space. Do you got it? Or confused? What about you, Najia? Are you still there?
Yes.
Okay.
So the difference only in axiom 10.
Yes.
Okay. But if we need to prove between not vector space and vector space, do we need to satisfy all the axiom?
If you want to prove a set is a vector space, so you have to show the 10
Oh.
axiom are satisfied.
Okay.
If you want to show that of a set is not a vector space, so you just find which axiom that fail to hold.
So axiom 10. Okay.
This on this case, on the axiom 10, depend our case.
Okay.
So it means if you want to show that a set is not a vector space, at least the set with this operation, at least one fail, uh, at least one axiom fail to hold. So you don't need to show that the others axiom satisfied. Just find which axiom that fails to hold. Okay, I have, wait. Oh. I have this exercise. I take it from the textbook. From number 1 until 16, we give a set. together with operation addition and scalar multiplication, you have to determine whether this set is a vector space. If it's not vector space, list the axiom that fails to hold, like I said before. For the example, number 1, we have n space here, 3 space here, x, y, z. With the operation addition, this is the standard addition, I think. Yeah, x plus x prime, y plus y prime, z plus z prime. Okay, this is the standard addition operation on 3 space. But for the scalar multiplication, it's not a standard operation. If you take a look at this, k times x, y, z, we get k times x. The second and the third component, same, without k here. So just be careful for this scalar multiplication. Can you guess for the number 1, is this vector space or not? If vector space, you have to show 10 axiom satisfy. If this is not vector space, just list or just find the counterexample. The counterexample that show which axiom fail to hold. Can you guess? Number 1, which axiom? Or guess first, this is vector space or not?
Not vector
No.
space.
Okay. Which axiom?
7.
7.
Wait, 7. What axiom? Alasan don't remember the axiom. 7. Axiom 7? Wait. After I'm closer. Okay, yeah. K times U plus V, right?
Yes. So we need to write the composition. It's like using axiom 7. It is not.
Yeah. Just describe here. So you guess. Wait, axiom 7, we have K times U plus V, right? Yeah.
Yes.
Are you sure? I think still okay, axiom 7. Okay, wait. Let K times x1, y1, z1 plus x2, y2, z2. So we have, K times x1 plus x2, and then y1 plus y2, and then the third component, z1 plus z2. So we have this, we have our definition, k times x1 plus x2, and the second and the third component, same here. I don't think so. This also satisfy. So we have k x1 plus k x2. We get k times x1, y1, Z1 plus, oh, sorry, plus oh, it's not enough. K times, wait, a bit. K times x2, y2, z2. Satisfy, right? Which axiom? If you take a look the last example, the previous example.
Because we see from k x y z equal to k x y z. From example 1, we solve from k, the behind of n, k x y z equals to k o x y and z. That's why we said that it's not satisfied axiom 7.
No, axiom 7 or another axiom. This for axiom number 7, right? Satisfy.
Yeah. Oh.
So we cannot say for number 1 fails on this the axiom 7. No, it's not. What if we have if you cannot guess, so you have to list starting from axiom 1. Okay, maybe this for your exercise. Try to solve it. We can continue on WhatsApp or our forum. Is there any question? Because our topic today only is vector spaces.
A bit confused actually.
What? Still confused where?
Okay. Oh, because I thought we need to look at the behind can x y z plus x prime y prime z prime and the rest is n k in bracket x y z bracket equal to k x y and z. I thought we look at the k y z to know that exam 7 is not satisfied.
Wait. Axiom 7?
Maybe we just don't know how to do. Yeah.
Wait, axiom 7, k times u plus v, right? This one, k times u plus v equals to k u plus kv. In this case, wait.
Because I thought it's become kx and comma and y.
X1, Y1, Z1, this is our U. And X2, Y2, Z2, this is our V, right?
Oh, okay.
So if we times K times U plus V here, okay, let's we cannot move this text, right? Or, wait, select. Okay. if you take a look at this, we have K, this is our U. Okay, maybe blue. This is our U, and this is our V. Okay?
So we no need to see at the K, X, Y, Z equal to K, X, Y, and
This
so
is
only this, okay.
the last equation to get K times U plus K times V, right? So the axiom 7 still hold. Still confused?
Okay, I got this.
Ah.
Why it give in the question? Why it give K, X, Y, Z equals to K, X, Y, and Z? What's the function of this? Can we look at the question?
Okay.
I just want to know what the use of
K, this is our operation, our scalar multiplication. Like I said before, if we have set with these two operation addition and scalar multiplication, depend on our case. In this case, we have addition operation is a standard, but not for the scalar multiplication, because our scalar multiplication here, k times x, y, z equals to kx, y, z. The second and the third component without k. We don't need to multiply the second and the third component by k. So this operation here, just follow this k times x1, x2. This is our u plus v, right? The first, the second, and the third component. If we times by k, if we multiply by k, so we get k times this first component. We have k times x1 plus x2. The second and the third, same, right? Without k. y1 plus y2, and the third, z1 plus z2. So from here, we multiply k times x1 plus k times x2. Actually, we missed one, we skip one step here. If you want to complete it. So from here we have k times, we have k times x1 plus k times x2. The second component, y1 plus y2. The third one we have z2 plus z1 plus z2. So from here, we just spread into two factor. We have k x1, y1, z1. Yeah. K times, k times x1, 1, z1, plus k times x2, y2, and z2 here. Oh. Okay, this is k times x1, y1, z1, right? Plus this one, k times x2, y2, z2. Okay. So be careful on this definition of weights. This definition of our expression. Okay. Any question or still confused? Maybe try it first, and then.
Perhatian. Sila ambil perhatian. Semua para penghuni tidak digunakan memesan makanan melalui perkhidmatan pesanan atas talian.
What kind of announcement there?
Cannot order Grab food.
Oh,
Yes.
they didn't provide.
Yeah, they provide, but maybe others needs extra food.
Oh, I see.
Yeah.
Okay. Is there any question? No. just try it first. If you got any problem, just ask me. Okay. Where is Nadia?
Yes.
Oh yes. Are you sleepy?
No.
Okay.
Ini adalah
Anyway, it's enough today. Thank you very much for your attention. Assalamualaikum warahmatullahi wabarakatuh and good morning.
Thank you.